This is Neil from Anabit, and in this video, we're going to cover how to make thermocouple temperature measurements using the ITS-90 standard. And what we cover in this video will be applicable to all different types of thermocouple sensors, but we'll have a special focus on the K-type thermocouple sensor since we'll use that in our demo and we'll use that in our code that you can access from GitHub. Here's the agenda for our video. We're going to give an overview of what a thermocouple sensor is, how it works, and its advantages over other types of temperature sensors. We're going to give an overview of the ITS-90 standard. We're going to talk about why making measurements of thermocouple sensor outputs is not easy. And then we're going to look at a demo that uses Arduino. It uses Anabit's precision logger, as well as code that's running the ITS-90 standard. And then we'll review that code to see how it's implemented. And like I mentioned, you can access that code on GitHub. So here is a quick overview of a thermocouple measurement. And there's various ways to generate electricity. I think there's like 6 or 7 different ways. One of those ways is the Seebeck effect. The Seebeck effect is real easy to generate electricity, but most people don't know about it because it generates such low-level electricity. And the way the Seebeck effect works is you just have to put 2 dissimilar metals together and you'll get a voltage potential. And if you have those 2 dissimilar metals in a closed loop, you'll actually get current flow. But this isn't too useful for everyday life because why? It doesn't generate a lot of power. But what we found is this Seebeck effect is very useful for measuring temperature, especially a large range of temperature, because the amount of voltage that putting 2 dissimilar metals together generates is really correlated to the temperature around those metals, especially where that junction of the 2 dissimilar metals meets, right? So if we know the 2 dissimilar metals, we can chart out their range of different voltage outputs related to temperature. So this is how thermocouple technology works. And there's different types of thermocouple sensors out there. There's T-type, S-type, J-type, K-type. And you can see I provided an example for K-type. You can see the 2 metals that are used, that where they combine, that junction is where we apply our temperature measurement, or where we use them as a sensor to measure temperature. And the benefit of them, like I mentioned, is they cover a large temperature range compared to most types of temperature sensors. Their disadvantage, though, is they don't have very high accuracy. When you take into all the effects, all the error effects, they typically only give you about plus or minus 2 degrees C, or maybe at best plus or minus 1 degree C. Okay, so what is the ITS-90 standard? ITS stands for International Temperature Scale. And the idea is this was done in 1990. This involved various government labs coming together and trying to come up with a consistent but highly accurate way to measure different temperature sensors. And thermocouples was one of them, right? And so the importance of using this standard is that it shouldn't matter if I'm buying a temperature measurement system from this part of the world and using it in another part of the world. All these measurements should be consistent if we use the standard. So that was the goal of the standard and why they did it. Now, for this demonstration, I'm going to be using data from NIST, the National Institute of Standard Technology. And I'm using this because I'm located in the US, and NIST is a US-based government lab. And so they maintain data for the ITS-90 that can be used for thermocouple measurements, specifically K-type thermocouple measurements that we'll use in our example. Now, they provide 2 different approaches, whether we're talking about the standard or NIST data. The first one is the lookup table. And the lookup table literally has a voltage to temperature value for every degree within the K-type thermocouple's range. If you make a measurement of a voltage, you can look it up in the table and you have the temperature. Very easy. The problem is, though, the table can be very bulky, so you got to store that in memory. You got to hard code that in memory. Also, the table only covers integer values of temperature. Then there's the polynomial approach. So that's what we're going to use in this video. Of course, I'll provide links where you can access information for both approaches, but we're going to use the polynomial approach. Why? It's very microcontroller friendly because you don't have to store a huge table in your memory. You do have to store some values that relate to our polynomial calculation, but you don't have to store a lot. And what's nice is the polynomial gives you values that could be fractional values of integers rather than just the integer values. Okay, let's talk about why it's not easy to measure thermocouple sensors. A thermocouple signal can be as low as microvolts. and as high as tens of millivolt range. But we need that resolution into the microvolts to make these measurements and make them accurate. Not only that, the signals are bipolar. That means the voltage values, depending on the type and the range you're in, could be positive voltages or could be negative voltages, right? So how do you measure that? You need a high resolution ADC, you need filtering. Why do you need filtering? Your thermocouple probe could be a long wire that's stretched out over a lot of distance. It could pick up, wireless signals as noise, high frequency noise. If you're plugged into AC line power, you could get 60 hertz or 50 hertz noise in your measurements. So high resolution, high accuracy ADC with multiple filter stages is what you need to make this measurement. The other part of a thermocouple that makes it tricky to measure is the thermocouple is all based on two dissimilar metals that you know about. If we connect the sensor to a board, we typically have to add another metal to the mix, whether that's a screw terminal connection, a crimp connection, or in my demo, I soldered the probe directly to the precision logger board. All that introduces new metals, which adds more Seebeck effects. Well, how do we deal with that? Well, we can apply the cold junction compensation to deal with this. The idea is if we make a temperature measurement at where this junction is, where the thermocouple metals that we know about are meeting the metals of our design, we can actually make a temperature measurement there locally and compensate for that in our code. And that's covered in our polynomials and in the ITS-90 approach, right? And it's often referred to as cold junction compensation. Okay, and here is the hardware we're going to use in our setup. So I'm going to use an Arduino, I think it's a Nano Every. Basically, the code I'm going to provide should run on any Arduino that supports hardware SPI communication, because that's what Anabit's precision logger uses for communication. So I'm showing Anabit's precision logger board, which you can access on anabit.co. And the idea is this has 5 differential measurement channels or up to 10 single-ended measurement channels. We're going to use it in a differential measurement standpoint because that helps reduce noise even more in our measurement. It also has an onboard temperature sensor that allows us to do that cold junction compensation. It also can support bipolar measurement. So here's a video of our demo. So what we're looking at is a toaster oven that Anabit uses for reflowing prototype boards. In there we have our standard. In there we have 2 thermocouple probes. We have a J-type that we use in there normally for monitoring the temperature in there. We have that connected to a data logger instrument. And we're just using that as a reference. So I'm not making things up, and that the temperature is actually referenced to a known good temperature reading. And then the metal probe is the actual K-type thermocouple. So now I'm going to shut the oven that is on and is producing some heat. Here is our setup. There is the precision logger. We have a differential channel setup. We have A6 and A7. That's where our thermocouple probe is connected. This wiring goes to our Arduino, the Nano Every that I'm using in this example, using SPI communication. Okay, here is our instrument that's making our reference measurement. So this is what the J-type thermocouple is connected to. And we can see we have about 67.2 degrees Celsius. And what you're going to notice is when I show this demo, the temperature is slowly rising because what happened is I opened the oven door and then I closed it. So the heat got let out, but now it's building back again. So we can see it clicking up right there, and then we can see our measurements from our Arduino code. You can see my computer screen is a little dusty, but here we're just printing things out to the serial monitor. Here you can see our thermocouple voltage that I printed out. It's 1.6496 millivolts, so you can see a very low voltage reading. Then we have our internal temperature sensor. This is used for our cold junction compensation. And so it's measuring 28.45 degrees Celsius locally on the board. And then we do our calculation. And once again, I'm going to show this in the code. But basically, when we calculate using our cold junction temperature and our thermocouple voltage, we get a reading of 67.63 degrees Celsius, which is what the temperature is inside my reflow oven or toaster oven. And you can see it just repeats. And like I said, it should be rising, right? So we see 67.6, we see 67.7, we see 67.8 or 0.9. So the temperature is going up because I just closed the door to the oven. And then we look at this temperature one last time, and you can see that this is slowly creeping up as well. We can see our code in action, that things are working because we have a nice reference instrument to compare our measurement to. Okay, now we're looking at our code that I will provide a link for in the video description so you can access it on GitHub. But right now we're just looking at the library or C++ class that I built that uses the data from the NIST ITS-90. And I will provide a link where I got this data, and so you can get it for K-Type, but you can also get it for the other thermocouple types. But I didn't make up this data. I got it from NIST's website. So these are used for our polynomial calculation, right? If we were using the lookup table, we would have a lot more values. But basically, in this array, this temperature to EVM, or temperature to voltage, this is the ones you use if you get a negative one. These are the ones you use if you have a positive. So this is converting temperature to voltage. Well, why do we want to convert temperature to voltage? That's for the cold junction compensation. Then we have voltage to temperature. We have A, B, and C. So these are our values. These are used for the polynomial equations, right? So let's go down to our polynomial equation. And this polynomial could be used in either direction to convert voltage to temperature or temperature to voltage, which we need for the cold junction compensation. Okay, so this is just our polynomial. I didn't make up this polynomial. I got this from the ITS-90 standard. Then we have our two functions that do our temperature to voltage and our voltage to temperature. And why do we need the first one? That's for the cold junction compensation. So first off, it checks the range to make sure you're within range. If not, it returns not a number. Then if your temperature is less than 0, negative, that tells you to use this array, and you can see we're calling our polynomial function. And then, of course, this double T is our input temperature. Once again, from the cold junction compensation. Then here is our function for doing voltage to temperature. So this is what we're going to use to get our thermocouple value. And first of all, we check the range. If it's below 0, then we use the array that's for negative. If it's below a certain voltage value, we use another one. So yeah, let me back up a second. This doesn't have to do with negative or positive temperature. This has to do with where the voltage falls in, you get different polynomial values, right? So that's why we have this A, B, and C array. And so based on where we are, our voltage measurement, then we apply the different array of constants to the polynomial, right? And how do I know these different voltage values? They're in the data that I got from the NIST website. And then finally, our last function is going to compute the final temperature. So it has two inputs. The first input is the thermocouple voltage that we measure. The second input is the cold junction temperature that we use for the compensation, where the thermocouple probe metals meet the metals on our measurement board. So we do two calculations, and we essentially are going to add that compensation to our thermocouple voltage. That's why we have to compute temperature to EMF or voltage. We add them together, and then we do our final calculation to get the finished voltage. Now, I'm not going to go over the whole Arduino sketch. It's pretty straightforward if you've worked with Arduino, but you can see my various printouts. And so I'm making voltage measurements. I'm doing the temperature compensation that I print out from the cold junction temperature. But really, here's where I'm using that final function call that uses the polynomial function. It uses the voltage to temperature, the temperature to voltage functions. That's being called here, right? So first I convert my voltage measurement into millivolts, and then I feed it into here. I make sure it's within range. If it's not, I print that out. If it is within range, I then print out the degrees in Celsius and the degrees in Fahrenheit. Okay, that's it for how to make thermocouple temperature measurements using the ITS-90 standard. And we also used an Arduino board, some Arduino code, which you can find a link for in the video description, as well as Anabit's precision logger. If you have any questions or you think I missed anything, use the comment section. You can also use Anabit's forum if you go to anabit.co. Thank you for watching.